Today we are going to pull back the curtain on an algorithm that is, no joke, one of the secret ingredients behind modern computing. You have probably never heard of it, but it's called Parallel Prefix Sum or JustCan. And trust me, it's the hidden superpower that lets your GPU just blaze through the enormous amount of data. So let's start with a simple puzzle. Think about a relay race. It's simple, right? Each runner has to wait for the baton from the person before them. But what if you had to make them all run their leg of the race at the exact same time? How could that possibly work? Well, that's the exact problem parallel prefix sum solves, and the solution is just incredibly clever. At its core, the problem seems almost laughably simple. We are just adding up numbers in a list, but as you are about to see, how you add them up changes absolutely everything. So, what is even a prefix sum? It's basically an operation where you take a list of numbers, say you have 3, 1, 7, and 4, and you turn it into a running total. The first number 3 stays a 3. The next one becomes 3 plus 1, 4. And the next one is 4 plus 7, that's 11. And finally, 11 plus 4 gives you 15. So, your list becomes 3, 4, 11, 15. Simple enough, right? Now, if you were just writing code for a normal single core CPU, this is a piece of cake. You just write a simple loop. You start at the beginning, and for each number, you just add it to the running total you had from the step before. It's super efficient. We call of this O(n) time, which is just a fancy way of saying if you double the number of items, you pretty much double the time it takes. Makes sense. But that simple innocent looking loop has a massive hidden flaw when you try to use something like a GPU, which has thousands of core, all ready to go and work at the same time. In this right here, this is the whole problem. To get the answer for the fourth item, you absolutely have to know the answer for the third. And for the thirds, you need the second. It's a chain. This data dependency, as the code says, is the death of all parallel computation. You can't have 1,000 workers ready to go if they all have to stand in a single file line waiting for the person in front of them to finish. So okay, how do you break the chain? Well, the first idea you might have seems pretty intuitive, but it actually ends up creating way more work than it needs to. So the idea goes something like this. We do it in the rounds. In round 1, every single element grabs the number 1 spot to its left and adds it. In round 2, every element grabs the number 2 spots to its left and adds it. In then 4 spots, then 8, and you keep going like that. In a few steps, everyone has the right total. It works and it's parallel, but it comes at a very big cost. And this is the cost. That simple loop we talked about does n additions for n items. This naive parallel way though, it does n times n log additions, and that extra log n might not sound like a lot, but for a list with say a million items, you are suddenly doing 20 times more total calculations. It gets the job done fast, sure, but incredibly wasteful. It's just not work efficient. But this is where things get really cool. A computer scientist named Guy Blelloch came up with this beautiful algorithm that solved the puzzle. It's a two-pass approach that is both fully parallel and perfectly work efficient. The big idea here is to stop thinking of the list as a straight line and start thinking of it like bottom leaves of a tree, or even better, like a tournament bracket. The algorithm does this two-step dance. First, there is an upsweep where it gathers up information from bottom to the top. Then, it does a downsweep where it passes the results from top back down to everyone at the bottom. This first pass, the upsweep, is all about reducing the data. It's just like that tournament bracket. In the first round, all the elements pair up and add their values together. This happens all at once in parallel. Then, you go to the next level up the tree, and those partial sums pair up and add their values. And this just keeps on going all the way up until the very last elements hold the grand total for the entire list. Let's actually watch this happen. Here's our starting array. In the very first step of the upsweep, every other element just adds the value from its neighbor to the left. See, the 1 becomes 4, the 0 becomes 7, and so on. And remember, all of these additions are happening at the exact same time. Okay. Now for round 2 of the upsweep, we go up another level in our imaginary tree. Now, elements that are further apart are adding their values. We are building bigger and bigger chunks of sums as we climb, collecting all the partial results we are going to need for the next phase. Alright, now for the truly brilliant part, the downsweep. We start by taking the grand total we just calculated at the very end of the array, and we just wipe it out. We set it to 0, sounds weird, but it's creating the starting point. We travel back down the tree, all using all the partial sums we calculated to hand out the correct prefix to every single element. So downsweep is all about passing information back down. At each level, parent node in our tree talks to its two children below. It basically passes a value down, and this information trickles all the way from the top of the tree down to the leaves, layer by layer in parallel. By the end, every single element knows the total sum of everything that came before it. And boom. After the downsweep finishes, the dependency chain is completely shattered, and we have our final result. And now this is what we call an exclusive scan, because each spot holds the sum of everything that came before it, but not including itself. And it's that little detail that makes it a powerful building block. And here is the real kicker, the punchline. This elegant algorithm, it's perfectly work efficient. It does exact same of n number of additions as that simple little sequential loop. No work wasted at all. But because of it breaks the dependency chain, it gets the entire job done in log of n time on parallel machine. You get the best of both worlds, maximum speed with minimum work. It's incredible. So, why do we care? Why go through all this trouble for a running total? Because once you have a really fast way to do a parallel scan, you suddenly unlock a whole bunch of other incredible powerful algorithms. You should think of a scan operation as superpower that other algorithms can borrow. It becomes the engine for ridiculously fast sorting, for complex image processing, for building huge data structures in parallel. So this algorithm is just a perfect example of how sometimes you need a totally different way of thinking to unlock incredible speed. It takes a problem that seems stuck in a step-by-step rut, completely opens it up. It really makes you wonder what other kind of things that we do sequentially usually are just one clever algorithm away from being completely reimagined in a parallel world. Just think about it. Bye.